Now, first of all, we have to define the heat. What is heat? Heat is a form of energy here, and heat is defined as a form of energy that is transferred across the boundaries of a system at a given temperature to another system at a lower temperature by virtue of temperature difference between two systems. Heat always moves from higher temperature to lower temperature. For instance, if we have a hot copper block placed in a furnace, we initially heated it to certain temperature using any kind of furnace, and we took the block out of the furnace and placed it in a room. Now heat will transfer from certainly the block is at higher temperature, therefore heat will transfer from the block to the surrounding, that is air and whatever the surrounding is. If you place it in a water, then water will be surrounding. So heat will always move from higher temperature to lower temperatures in the direction of positive gradient. That heat is transferred from the system at a higher temperature to a lower temperature, and heat occurs solely because of the temperature difference between two systems. If there is no temperature difference, then there will be no heat. There will be no transfer of heat. There will be no motion of heat, whatever you want to say. There will be no heat. Heat is also a transient phenomenon. It cannot be defined as a property of the system. So heat is only defined when it crosses boundaries. So another aspect of the heat is that the body never contains heat. Rather, heat can be identified only if it crosses the boundaries. Thus, heat is transient phenomena. If we consider the hot block of copper as our example, and the cold water in the beaker is another example, and we now put the hot copper block in the beaker filled with water. The heat will only be defined when it will be transferred from copper to surrounding. Now, initially assume that the copper block is at let's suppose 400 degrees centigrade, and our beaker is on room temperature, let's say 25 degrees centigrade. When we initially put the block in the water, because of the temperature differences, the heat will move from copper to water, and it will continue to move until the water reaches the same temperature as of the copper block. Now the temperature of the copper block will continue to decrease, and temperature of water will continue to rise, and they will meet at a conjunction that is defined as the thermal equilibrium. Now thermal equilibrium, as we have already discussed in the classes, on-campus classes, that yeah, thermal equilibrium is defined when there is no temperature difference between two bodies. So we can say that the two bodies are in thermal equilibrium with each other. So heat is only defined when the copper block will have the same temperature as the water in the beaker, then there will be no motion of heat, and we cannot define heat at that point as a property of system. So heat can never be defined as a property of system. So the heat is a form of thermal energy. There are various forms of energy, as we already know. So heat is associated with the thermal aspect of the energies. And if we want to quantify the heat, then we would require certain units. For example, in international system, the unit of heat is joules. It and The joule is defined as and there is another unit of heat that is known as calorie, and calorie is defined as the amount of heat required to raise the temperature of 1 gram of liquid water from 14.5 degrees centigrade to 15.5 degrees centigrade by a difference of 1 degree centigrade. So we also can define the calorie is the specific heat of water at 14.5 degrees centigrade, or nearly 14.5 degrees centigrade. So if we want to heat the water from liquid water uh, from 14.5 degrees centigrade and to 15.5 degrees centigrade, there's a 1 degree temperature difference. We will You will note that this is the same definition of specific heat. So we can also say that the calorie is specific heat at constant volume of a liquid water at 14.5 degrees centigrade. We have already discussed, and we will also discuss in next slides, that the specific heat is a function of temperature. So specific heat is not constant; it varies with temperature. So we will discuss it in later slides. Similarly, if you want to define the kilocalories are amount of heat required to raise the temperature of 1 kilogram. Previously, it was 1 gram in the case of calorie. Now it is 1 kilogram of water, liquid water, to raise temperature from 14 degrees centigrade, 14.5 degrees centigrade to 15.5 degrees centigrade. It is known as kilocalories. There's another unit of heat, that is British thermal unit. It is defined as, now to understand the British thermal unit, consider the same system of a hot copper block and a beaker filled with water. Now consider that the water is initially at 59.5 Fahrenheit, and the amount of water in a beaker is 1 pound. When we put in the hot copper block, the raise in water temperature is 1 Fahrenheit, that is 59.5 to 60.5 Fahrenheit. Now the amount of the heat that is transferred from the copper to water to raise this temperature from 59.5 Fahrenheit to 60.5 Fahrenheit is the amount of heat that is equal to 1 British thermal unit. Now consider let us talk about the modes of heat transfer. So there are three basic modes of heat transfer, that is conduction, convection, and radiation. For the conduction case, we know that the molecules have kinetic energy, rotational energy, vibrational energy. So there is a certain amount of mechanical energy that generates linear velocity, rotational velocity, and vibrational motion in the molecules. So this molecule in any solid uh, strikes its neighboring molecule and transferred energy, some of its energy, to the neighboring molecule. This form of energy that is being transferred from molecule to other molecule, while both the molecules maintains their initial position, they only strike each other, they strike neighboring molecules. This form of energy transfer is recognized by conduction as the conduction heat transfer mode. So if we want to consider an example, let us consider an example of a solid aluminum rod. This solid aluminum rod, is placed on a fire of certain flame. Let's say the natural gas flame, and let's suppose this end of the rod is at 400 degree centigrade, and the other end of the rod is placed in an ice bath having temperature of 0 degree centigrade. So heat will transfer from 400 degree centigrade to 0 degree centigrade and the molecules, if we take an magnified magnified view, if we take it and we consider these molecules, and again we consider these two molecules and rotating and vibrating at a frequency and banging its neighboring molecules, uh, and transferring energy in this form. This is conduction heat transfer mode. It is recognized as a mode of heat transfer and named conduction. The second heat transfer mode is convection, and in convection, the molecule physically uh, moves from one position to another and carries energy with it. And this form of heat transfer is uh, known as heat convection. For example, we considered hot copper block example when defining the units of heat, and we we put a hot copper block in a beaker filled with water. Now the now if we consider the hot copper block being placed in this beaker filled with water, and here hot copper block is placed, and if we magnify this wall and talk about water molecules, so this molecule will physically move. It will take energy from the wall, and it physically moves upward. This molecule will be replaced by another molecule, and this will generate a motion in the medium in which the molecules change their initial position. This mode of heat transfer is known as convection, where the medium facilitates heat transfer by its motion. And there are two forms of heat convection. One is free convection or natural convection, and the second one is forced convection. Now, let us define what is free convection and what is natural convection. Free convection is the what we have considered in this example, that we have a solid copper block, and molecules of water are not forced by any physical means. For example, we have not placed a propeller over here that generates a water current and forces the molecule to strike this wall and take energy and complete this phenomenon. No, we didn't use a propeller or any sort of source that generates the motion of medium. So this is, if we don't use uh, any any source, and we do not force the medium to move, it moves by itself. It moves because when this molecules takes energy from the wall, and there will be a local difference of densities. of a hot medium and a relatively cold medium over here, let's suppose. So because this portion of medium will have higher density, so the molecule will move down because of higher density, and this low density molecules will move upward. This is called natural convection. On the other hand, if we consider forced convection, for example, we have a heat exchanger, and we have this shell and tube heat exchangers, in which we have these different tubes. We have these tubes, and let's suppose water at 40 degrees centigrade enter it, and we use enter these small tubes. In this big tube, there's water at 0 degrees centigrade. There's water in 0 degrees centigrade, and what we are doing is we are forcing this water to enter, this cold water to enter from here and leave this. So if you look into the cross-sectional view, this big tube, and there are small tubes in it. In these small tubes, there's water flowing at 40 degrees centigrade, and another liquid, that is water at 0 degrees centigrade, or 10 degrees centigrade, that is relatively cooler than 40 degrees centigrade, is moving in this shell. There are tubes, small tubes, and then there's a big shell. For water at 10 degrees centigrade, cold water in the shell, and water at higher temperature, 40 degrees centigrade, in the tubes. Now we are using a pump. We are using a pump to pump this cold water, and obviously this hot water as well. Now we are forcing the uh, molecules of cold water to strike these tubes, wall of these tubes, using pump. So we are using, and move on, a new molecule will replace it, but we are forcing this new molecule. We are generating this motion of water to expedite, to facilitate, to enhance the heat transfer. So this type of heat transfer is known of heat transfer, or this type of convection is known as forced convection. Now there is another form of heat transfer, that is heat transfer because of radiation. And radiation heat transfer. In radiation heat transfer, we do not require any medium. For example, in convection and in conduction, we discussed examples that the heat is being transferred from higher temperature to low temperature using aluminum solid rod. Solid rod is a medium, and then in convection we considered an example in which we placed a hot copper block in a cold water medium, and the water takes the heat and do the work. This type of heat transfer requires certain medium to transfer the heat from higher potential to lower potentials. However, in radiation, we do not require any source of medium, any sort of medium. For example, uh, for example, this let us draw a globe. This is this is Earth. If we can draw it as well as we can. So this is Sun. So the radiation is the main cause that we are getting energy from Sun to the Earth. While there is no medium in between Sun and Earth, heat is heat is being transferred from higher temperature, that is Sun, to low temperature of Earth, but there is no medium in between. So this type of heat transfer is called radiation heat transfer. It depends on it only depends upon the temperature difference. For instance, uh, we have a radiation source over here, okay, and then we and its temperature is 400 degrees centigrade, and then we have some body over here that has a temperature of 10 degrees centigrade. Now the radiation will and there's no medium in between. The amount of heat transfer that will transfer from this higher temperature to lower temperature using radiation only depends upon the temperature difference. This 400 degrees centigrade and 10 degrees centigrade. There is a temperature difference of 390 degrees centigrade. It exactly not depends upon the temperature difference. It depends upon the temperature difference after taking its power to the 4. Now we will discuss it in the next coming slide. So, what is the temperature of higher body? What is temperature of lower body? The greater the temperature difference, the greater will be the heat transfer because of the radiation. It also depends upon miscibility. And what is the miscibility? Let us discuss shortly. And then there's the frontal area, that what is the exposure area of this between these two bodies. If there's a certain hindrance in between, for example there's a wall in between, then there will be substantially low amount of heat transfer depending upon the material of this wall. Either it allows the radiation to pass or not. Uh, if there is less exposure area, lesser the exposure area, lesser will be the heat transfer because of the radiation. So what is emissivity? Now in this slide we can see different images that are being generated by thermal imaging camera, and it senses the radiation that comes out of the body. So we can see that there are different pictures, a picture of a lady, some guys coming out of a gallery, a dog, a hand, and automobile vehicles at road. We can see that how the thermal imaging camera senses and generates these images. It takes the radiation coming out of the body, and it puts that radiation in a perspective, and do the math, and let us see these pictures. We can measure temperatures using these non-contact type sensing techniques. We can see that the engines are heated because of its temperature. They are then the front portion of car is bright yellow, and there's less amount of thermal energy in the cabin, so it is like purple or black. So we can see the human hand is also generating certain radiation. Humans are generating, animals are so every material, either engineering or non-engineering, it generates the heat, it generates the radiation. Sometimes it falls in human visible capability to view the color. Sometimes it's not, but the material generating the radiation, this is emissivity. So emissivity is the capability of the temperature of a body to emit the radiation at certain temperature. Higher the emissivity, higher the radiation heat transfer. Lower the emissivity, lower the heat transfer because of radiation. Now the formulas for heat transfer because of conduction, convection, and radiation are presented over this slide, and you can see, and we will discuss the what is K. K is the conductive heat transfer coefficient. Higher the conductivity of material, higher the value of K. A is the cross-sectional area from which the heat flux passes. D and T, dt or dx is the temperature gradient. What is the temperature difference of two bodies, and what is the distance between them? In the convection, H is the convection heat transfer coefficient. It depends upon a lot many things, and you will calculate heat transfer coefficient because of you will discuss, you will learn convection heat transfer coefficient in detail in another course, that is heat and mass transfer. Then is A. What is the area where molecules are being forced unnaturally hitting the surface and taking the energy from it and moving on? In convection, we know that a medium moves in the heat convection. So what is the area? For example, the a particular example we considered in convection was the block of hot copper placed in a beaker filled with water, and water molecules are taking heat. So the walls of hot copper block, is the area from where the molecules are taking the energy. So A is that area. T is T infinity. What is T infinity? T is infinity that if we have uh, this copper block wall, and obviously it was on 400 degrees centigrade as we discussed. Now molecules near to it will have more thermal energy than the molecules relatively away from the wall, than the molecules from far away, than the molecules far away. So there will be temperature difference between this molecule layer, this molecule layer, and this molecule layer. There will be temperature difference, spatial temperature difference depending upon the space coordinates. So if we keep moving away from the body, then we will come at a point then that there will be no further temperature difference between these layers of molecules in a water medium, as we have considered in this example. So what is the temperature, or have we take as T infinity? Okay. For example, if we take a copper block and put it at 400 degrees centigrade and put it in a room on a table, and initially the temperature of room was 25 degrees centigrade. So now if we keep moving toward the copper block, we will observe that the air will keep getting hotter until the temperature of the molecules that is colliding uh, the surface is 400 degrees centigrade, nearly 400 degrees centigrade. So the more we move toward the block, it will be getting hotter, and if we move away from the block, then we will come at a point where if we move further away, there will be no temperature difference, and this temperature is known as T infinity. T surface is definitely the temperature of copper block. Then there is radiation heat transfer, and we can say that there is emissivity epsilon, and there's the Stephen Boltzmann constant, there's exposure area, as we have discussed in previous slide, and T4. What is T4? For instance, um, T4 is low temperature, the body of low temperature. Body at low temperature is T infinity in this case, and T surface is the body at high temperature. And we can see that we take the power of 4 and then we take the difference. These are formulas we use for heat transfer. And you have noticed that there's a dot over Q. Q is heat conduction, there's a dot over it here. Q dot. What is Q dot? Q dot is rate of heat transfer. By using these formulas, we can predict, we can calculate and estimate the rate at which heat is being transferred from higher temperature and lower temperature. Not exactly the value of heat. It will be the watt, joules per second, calories per time. So these are formulas to calculate the rate of heat transfer, not the amount of heat that is being transferred. We can integrate it over the time, and we can calculate the amount of heat that was transferred. But these formulas estimate the rate of heat transfer, not the heat transfer.